This is Lab 1 Constant Velocity for Physics 2211. Here's what I'll be covering in this presentation and video. The purpose of this lab is to apply Newton's first and second law to objects we interact with in our day-to-day life. This will be done by observing and analyzing the motion of an object that is moving at a constant velocity over a period of time, creating a computational model based on the analysis that predicts the position of the object, and then comparing the experimental and predicted position data using physics principles. These principles include Newton's first law, which states that an object at rest remains at rest, or if in motion, remains in motion at a constant velocity unless acted upon by a net external force. This means that constant velocity occurs when net force equals zero. Another important principle includes Newton's second law, or the momentum principle. This focuses on the fact that surrounding forces acting on a system can cause changes in momentum over time. Derived from Newton's second law are two important formulas, the velocity update formula and the position update formula. Note that in this experiment, since we are dealing with constant velocity, F net for the velocity update formula needs to equal zero. For this experiment, I chose to use a massage roller as my object, also known as my system, and used a hardwood floor as my surface. In terms of the surrounding, this includes forces such as friction, gravity, the initial push from my hand, and more. Some important measurements to make note of include the mass of the roller and the diameter, which I use later to calibrate tracker and input into the GlowScript code. At the end of this experiment, we'll see that both the observed and predicted models produced linear graphs that shared similar slopes, implying that the velocity was constant. However, near the end, the observed line began to deviate slightly from the predicted line, suggesting otherwise. The first part of this experiment includes video analysis and data collection with tracker. Here you can see the video clip I selected to track the motion of the roller. I chose the time that was a bit after the initial push in order to select a period where the object was moving closer to constant velocity. As mentioned earlier, I used the diameter of the roller for calibration, and the initial position is listed here on the side, as well as the second position taken after 33 thousandths of a second, which will be used later to calculate initial velocity. The final observed time is also something I will use later for the GlowScript code. Other things to know is the movement of the object, which is from right to left, or the negative x direction. This results in a negative downward slope, as you can see on the graph. I also made sure to set the origin at the center of the roller at the initial position and time. Moving on is the computer model and predictions through GlowScript. Here on the left, you can see that I used the initial and final positions and time from before to calculate the initial velocity. This is used to set the initial conditions for the code. On the right is the calculation while loop, which runs for as long as t is less than 1.53 seconds, which is the final observed time from before. Here I set fnet equal to 0 for constant velocity, and you can see underneath are the velocity and position update formulas that were introduced earlier. So here's the model produced and the corresponding position versus time and velocity versus time graphs. As you can see on the left, the ball is moving towards the left, resembling the motion of the roller. The lines on the right display the constant velocity. The position versus time line is decreasing at a constant rate, and in the velocity versus time graph, you can see that this rate or velocity stays at negative 0.34 meters per second. Now we can compare the two models. The dotted line is based on the observed data, and the straight line represents the predicted data from the computational model. Both lines have the same initial position and velocity overlapping in the beginning. However, as time progresses, you can see that the observed line begins to deviate from the predicted line. This deviation is somewhat expected. The computational model does not account for surrounding forces, except for perhaps gravity, since it is balanced out with the normal force. The observed data is affected by surrounding forces such as friction. However, this also means that if there was a change in velocity, velocity should be decreasing and not increasing as implied on the graph. While there is only a difference of 0.013 meters per second for the slopes, this increase in velocity is something that should be noted. Possible errors may include uneven floor surface, not rolling the roller straight, placing points when tracking, inaccurate calibration, and more. So what if we flip the x-axis? As mentioned multiple times already, the current data is graphed below the x-axis, with a negative slope due to the object's leftward movement. Flipping the x-axis would indicate a rightward movement, producing a positive slope above the x-axis. Velocity will become positive because it is a vector, which has both magnitude and a direction. Speed, on the other hand, will not change because it is a scalar and will stay positive. Also, would it be possible to determine how many forces add up to give zero net force? Well, in this real-world scenario, zero net force was not observed, as there was a change in velocity. However, even if there was a net force of zero, there are many forces that are present in the surroundings, some big, some small. Too many to be able to account for and determine the exact forces present that ultimately add together to get zero net force. In the computational model, though, we can perhaps simplify the forces down to 4 that add up to a net force of 0. Gravity, which works in the negative y direction, should be equal to the normal force in the positive y direction, and assume that the push in the negative x direction is equal to the friction force in the positive x direction. So to conclude, in this lab we were able to analyze and visualize the motion of a roller moving the negative x direction using Tracker, and then compare it to a computational model in GlowScript that predicted the position given the initial velocity. This was done through the understanding of Newton's first and second law of motion, which helped with calculating future position and velocity. Finally, it is important to note that while computational models are helpful in producing and predicting data, they don't necessarily take surrounding forces into consideration.